Yes, good afternoon. Welcome to this tutorial class for SCH 102. And I was not able to be with you yesterday because I had an important engagement, but all the same, I sent to you the recording of the same tutorial class which I had last year for the student who did SH 102 last semester. So it is covered in there and you'll be able to find the discussion in there. But today I will start by discussing with you first how to draw Lewis structures. And as we do so, of course, if some of the compounds happen to have resonance structures, we'll also have a look at them. So what I want us first to do is to draw the Lewis structure of these four molecules: CH2, NNH2, HNO2, sulfuric acid, and ozone. That's what I want us to have a discussion on. Can you see my slides?
Yes.
Okay.
Yes.
And it is what I want you to know. It is a tutorial, okay? So it should be participatory. And as we participate, I want you to interact with me, but you will only unmute your mic when you have something to say. Otherwise, let it remain muted because as it will bring a lot of echo, okay? So what I want to discuss with you, as I said, is we want to have, from the assignment, I have given you, I have picked some problems, probably some other problems which are also not in the assignment. I have outlined them here, which I believe are going to be instructive. So the first one we are going to look at is the Lewis structure of this molecule, CH2NNH2. Can you see this molecule?
Yes.
So what I want us to do is draw its Lewis structure, okay? Drawing Lewis structure is not a guesswork. We follow certain principles and certain steps. So in drawing Lewis structures, we have seen there are a number of steps. So the first step, step one in drawing Lewis structure is to arrange the atoms. You arrange the atoms. Arrange the atoms. And when we arrange the atoms, we are not doing it casually. We follow some basic principle. One of the things we follow is one, put the least electronegative element, the least electronegative element at the center. It works most of the time, except there are some few exceptional cases which we may not come across in this unit. So put the least electronegative atom at the center. The least electronegative atom at the center. So the other thing, of course, put hydrogen and halogens on the outside. Okay, these are the basic rules we follow. So now when you look at this molecule, CH2NNH2, in this molecule, we have carbon, 2 nitrogens, and 4 hydrogens. So when you look at this, so we have the hydrogens that has to be kept on the outside. And the way this thing is arranged, it is given as an indication on which element is next to which one. So what we are going to do, we put carbon, and then on the carbon or around the carbon, we have 2 hydrogens. Then we have a nitrogen, and next to that nitrogen, we have another nitrogen. Then on this nitrogen, we have 2 hydrogens around it. As you can see, the hydrogens are on the outside. And we have carbon, which you can almost say at the center, bonded to 2 hydrogens and a nitrogen. And then we have a nitrogen that is bonded to a carbon, to another nitrogen, and then a nitrogen that is bonded to 2 hydrogens. So this is what is determined in step 1. We determine the arrangement of the atoms. What is the next step? Can you tell me what the next step is?
Counting the total number of valence electrons.
Thank you very much. So step 2. So it is good you follow steps. When you are doing everything, you do it logically. You don't bring the answer from somewhere. You have gone through a process in obtaining the answer. So you must show it, okay? Count the total number of valence electrons of all the elements that are in this molecule. So we have hydrogen, and then the number of hydrogens we have are 4. We have 4 hydrogens. We have 1 carbon and 2 nitrogen atoms. These are the elements we have in this particular molecule which are bonded. So we have 4 hydrogens, and the valence electron of hydrogen is 1. Hydrogen has got 1 valence electron because it is in group 1A of the periodic table. So the number of valence electrons as a result of the 4 hydrogens is 4 electrons. Then we have 1 carbon, 1 times carbon is in group 4 of the periodic table. It has got 4 electrons. So the total number of valence electrons contributed by carbon in the formation of this molecule are 4 electrons. Then nitrogen, we have 2 of them. Nitrogen is in group 5A of the periodic table. The number of valence electrons of nitrogen are 5. So 2 times 5, 10. 10 electrons. Now, when you add them up, this one will become 18 electrons. As you can see, the molecule, this molecule is not a charged molecule. It is neither positively charged nor negatively charged. So this will remain the total number of electrons. Okay, so let me pick this one as we go to step 3. What should step 3 be? What is step 3? Hello?
We add the bonds and lone pair of electrons.
So you add bonding and non-bonding electrons. So we have a total of 18 electrons. We have 18 electrons. These are the total number of electrons, 18. So this was determined in step 2. And this one was determined in step 1. So we are progressing. So now, from what we have gotten from step 1, we have a carbon. And this carbon is bonded to 2 hydrogen, is next to 2 hydrogens. And then we have a nitrogen. And then another nitrogen. Then on this nitrogen, we have 2 hydrogens. So what we do first is add bonding electrons, because there is a chemical bond between this carbon hydrogen, between this carbon nitrogen, etc. So we must form a chemical bond between these atoms using a single bond. So you take and form a bond between the carbon and hydrogen, this carbon and hydrogen, this carbon and nitrogen, this nitrogen and this nitrogen, this nitrogen and hydrogen, this nitrogen and hydrogen. This is the first thing we do. Okay? Now, how many electrons have we used when forming single bonds between all the atoms in this molecule? How many electrons have we used?
12.
12, because we have formed 6 bonds. 1, 2, 3, 4, 5, 6. We have formed 6 bonds, 6 single bonds, which basically means 6 times 2, 12 electrons we have used. We have, out of the 18 electrons we have used 12 of them. We must use all the electrons. So the balance we have, the balance of electrons we have, balance of electrons will be 18 minus 12, which is 6 electrons. We have this balance remaining. Okay. Now we use these remaining electrons to fulfill the octet of the elements in this particular molecule that do not have octet of electrons. So if you look at this carbon, it has 3 bonds with this carbon, with this nitrogen, with this hydrogen, and then with that hydrogen. What is the total number of electrons you see on this carbon? What is the total number of electrons on that carbon? Hello?
6.
6 electrons. 6 electrons. How about on the nitrogen? How many electrons do we see on the nitrogen?
4.
How about on this nitrogen?
6.
So none of
6.
these elements, none of them have octet. No octet. All these ones, they do not have octet of electrons. Okay? We have 6 electrons. Then we have to use these electrons first as a lone pair to see if we can satisfy the octet of all the elements. Okay, so what are we going to do? is, let me take this one on another page, if I can. Okay, I can redraw it, okay? I can redraw it. I have carbon, nitrogen, nitrogen, which is bonded to a hydrogen on this side, to another hydrogen on this side, and hydrogen and hydrogen. Balance of electrons is balance of electrons is 6. Now we have to use these 6 electrons to fulfill the valence, the octet of the carbon, this nitrogen in the middle, and the nitrogen on the outside. So what we need to do first is to fulfill the octet of the element that are on the outside, not at the center. You first forget about the central element, which is this nitrogen. We forget about it. First, we see to satisfy the octet of this carbon and the octet of this nitrogen. How many electrons will this carbon require to have octet of electrons? How many electrons will this carbon need? How many electrons?
2.
So we'll put those 2 electrons in here, okay?
Yes.
2. How about this nitrogen? How many electrons would it need to have octet of electrons?
2.
This
2.
one also require 2 electrons, okay?
Yeah.
We have a balance left. Do you have any electrons which we have not allocated?
Yes, 2 remaining.
2 remaining.
2 remaining.
Okay? So the remaining 2 electrons, where do we take them? We give it to the central nitrogen, this one.
Nitrogen.
Okay? The central nitrogen. Now, we have used all electrons are used. All the valence electrons are used. But one of the elements, despite this, okay, one of the elements does not have octet of electrons. It does not have electrons. This nitrogen, as you can see, how many electrons do you see on the nitrogen?
6.
Only 6 electrons. This one does not have octet. It does not have octet. No octet.
6 electrons.
Only 6. Then how can we now achieve? How can you make sure this nitrogen also has octet of electrons? How can we do that?
Add another bond.
How?
Form a double bond between carbon and nitrogen. The first carbon.
Between this carbon and nitrogen. So let me just look at it, okay? I like how you think, and this is how we should think. So let's do it like this. We take this lone pair of electrons, okay? This lone pair of electrons, and form a double bond in here, okay? So when we do that, what we'll get is this molecule. We have a carbon that has got a double bond with a nitrogen. Then on this nitrogen, we have lone pair of electrons. Then we have another nitrogen, which has got lone pair of electrons. And then it has got 2 hydrogens on it. And then we have this hydrogen and this hydrogen, okay? So when you look at this is a valid Lewis structure. Valid Lewis structure. Because we had 18 electrons. We used all of them. Let's count. Okay, 1, 2, 3, 4, 5, 6, 7 bonds. Okay, as a result of the 7 bonds, we have 14 electrons. Okay, 15, 16, 17, 18. All the 18 electrons are used. Then if you look at the hydrogen, it has got duet of electrons. If you look at the carbon, has got octet of electrons. If you look at the nitrogen, it has got octet of electrons, the middle nitrogen. If you also look at the other nitrogen, it has got also octet of electrons. So this is a valid Lewis structure. Okay? Are you satisfied?
Yes.
Yes.
Excuse me, sir.
Yes. Yes.
So the one who said, excuse me, ask me, dear.
May I ask that why don't we remove the 2 electrons from the second nitrogen, but rather remove
Okay,
the 2
so you are saying,
electrons?
okay, good. I understand you, and then I was expecting such a question. Thank you for asking. Okay, so
Yeah.
you are saying, instead, why can't we use these electrons, and form a double bond with this, isn't it? So let me use a different color so that we can follow these things. Okay, let me use this. Suppose we use these electrons. Okay, suppose we use these electrons and form a double bond. Okay. Now let us look at what structure we get. Okay, and then we evaluate the 2 structures, and then we say you're not this one but that one. Okay, so now when you look at this, what you should know, first let me concentrate this on the nitrogen here. I have a lone pair of electrons, the nitrogen in the middle. Then I have a double bond on this side. Okay, then a hydrogen here. And then on the other side of the carbon, we have a hydrogen, and a lone pair of electrons. Okay, this is what is going to happen, isn't it? Cindy?
Yes.
Yes.
Now let's evaluate the 2 structures. I want you first of all to look at the structure in red. Does it have any atom in this molecule? Is there any atom in this molecule that is charged positively or negatively in this one? None of them, isn't it? Because carbon has four bonds, nitrogen, each of the nitrogen have got 3 bonds, the hydrogen 1, none of them. But if you look at this one, this nitrogen, since instead of the usual 3 bonds, it has formed 4 bonds. And then if you calculate the formal charge on the nitrogen, you'll find the charge on this nitrogen is +1. So this is +1. This is plus. Then if you look at the carbon, then we can calculate the formal charge for this carbon if you want. Formal charge on the carbon, formal charge is equal to number of valence electrons. The number of valence electrons of carbon is 4 minus. Okay, how many lone pair of electrons do we see on the carbon? We see 2 plus half of the bonding electrons. You see in the carbon, we have 1, 2, 3 bonds. And then each of the bonds are as a result of overlap of 2 electrons. So the total number of bonding electrons are 6. like this. So when you calculate the formal charge, it will be 4 minus 5. 4 minus 5 is minus 1. So what this will do, it will put a negative charge on this carbon. And then a positive charge on. Which of the two Lewis structure is outrightly stable? Which one is more stable? Because
The one with no formal charges.
the one with no formal charges is very stable. But this one, it's got a lot of charges, it's very unstable. That's not how the molecule is. Okay? So the molecule, this molecule is not about even resonance. This one does not exist at all. There is nothing like this. Okay? The structure of the compound is this. So it's not a problem that we can think it is possible. Yeah, I can do this and I can do that. Okay? Then you investigate them and then find which one is the most stable. So the most stable one is one that does not have charges. Okay? That has less separation of charges, all sort of things, because the presence of charges make molecules to be very unstable. So there is no doubt about this, that the structure of this molecule is what is written in red. Is it okay? Are you satisfied?
Yeah, I'm okay now.
Yes. Thank you very much. So now,
Thank you.
yeah, Karibu Sana, it is my pleasure. Okay, don't worry. I want you to ask question and I feel very happy. If you don't ask question, I get very, very worried. Okay, so let's look at the second example.
Excuse me, sir.
Yes.
I was asking, when you're drawing this Lewis structure, must you obey the hybridization, or
No,
it's just okay not to obey?
no, hybridization has got, in Lewis structure, we only worry about which atom is next to which one. We also worry about what kind of bond we have between two atoms, double bond, single bond, triple bond, which element has got lone pair of electrons, which one has got a charge, positive, negative. That's all. Okay? We don't worry bond angle, we don't worry about other things. Is it okay?
Yes, sir.
Thank you. So let us now draw the Lewis structure of this molecule called HNO2. So I like following steps. I want you to be neat. When you are doing your work, you must do it neatly. Neatly means you must have logic. You don't bring an answer out of the blue. There is a thought process that was used to arrive at the answer. So the first one, step one, is arrange the atoms. Arrange. You take your time in arranging the atoms the correct way. If we had arranged these atoms of CH2 and NH2 differently, it will be a totally different structure. It will be a wrong structure. So I don't want you to assume this to be an easy step. It's a most important step because the rest of the process will be based on that. So you must arrange the atoms. Okay? Now, when you are arranging the atoms in this particular molecule, which one should come? Which one should be outside? Huh?
All hydrogens and oxygens should be outside.
Why?
Because nitrogen is less electronegative than others.
You know me, I can see I have taught you very well. I'm feeling proud. So So hydrogen should be on the outside, okay? Hydrogen. So hydrogen will be on the outside, no doubt about it. So in this molecule, we have nitrogen, and then we have oxygen. Which one should be at the center?
Nitrogen.
We are very sure about the hydrogen. The hydrogen is on the outside, okay? Nitrogen, because it is less electronegative compared to oxygen. Okay? So even when you are answering questions like this in this unit or any other, don't just assume. Whatever you think, write it, okay? Write it. So we'll have hydrogen on the outside, of course. Now we'll have oxygen. We'll have a nitrogen. You will have another oxygen. So the hydrogen, as you can see, is on the outside. So we have the two oxygens and the nitrogen. So we have decided to put the nitrogen in the middle because it is the least electronegative atom. So that's what our decision, okay, logically. So what we do next is, what is step 2?
Count the
Step 2 is,
total number of valence electrons.
yes. So let me draw this nicely. Let me draw it like H, so that the molecule we draw at the end of the day looks neat. Let me draw it again, sorry. But all the same, it does not matter. Oh, let me not worry about this. So let's just step 2. Step 2. Count the total number of valence electrons. All the elements in this molecule, we count the electron, the valence ones, okay? So we have a hydrogen, we have 1 hydrogen, we have 2 oxygen, we have 1 nitrogen. For hydrogen, the number of valence electrons is 1. 1 times 1 electron. For hydrogen, it will be 1 electron. For oxygen, it will be 2 times 6, because oxygen is in group 6A of the periodic table. So the total number of electrons that are contributed by the oxygens are, by the 2 oxygens are 12. And then we have 1 nitrogen. 1 times 5, because nitrogen is in group 5A of the periodic table, 5 electrons. As a result, the total number of valence electrons of all the elements in this particular molecule are 18. Please mute. Hello? Mute your mic. Unless you are saying something, okay? Because it will disturb all of us later on when we listen to the recording. So this is arrangement and the total number of electrons. This is from step 1. From step 1, and then from step 2, we have obtained 18 as the total number of valence electrons. Then step 3 is add add bonding, add these electrons as bonding and non-bonding electrons, or lone pair. So the non-bonding are lone pair of electrons. So now we have hydrogen, we have oxygen, we have nitrogen, we have oxygen. The first thing we have to do is form a chemical bond between them to say that this is a molecule and there are chemical bonds between them. So how many electrons have we used? Number of electrons used are
6.
6. Balance
12.
12. Okay, the balance is 12. Now, when you look at the elements, of course, hydrogen is happy because it has got weight of electrons. If you look at this oxygen, it has got only 2 bonds, 4 electrons. If you look at the nitrogen, it has got 2 bonds, 4 electrons. The oxygen has formed 1 bond, only 2 electrons. So none of these elements have octet of electrons. It's no octet. Okay, so we have to satisfy the octet of this. Okay, so what I will do, just pick this, this one, and take it to another slide. I will share with you the slides, okay? Don't worry. We have 12 electrons, and there are some element whose octet is not fulfilled. So now we have to use this balance 12 electrons, this balance 12 electrons to fulfill octet, okay? So we do first for which ones? For the nitrogen or for the oxygens? Hello? For the nitrogen or for the oxygen? Eh? Okay, for the oxygens, because oxygen is on the outside. See, when you look at this element, we know very well we have this oxygen, this nitrogen, and this oxygen. All the 3 of them, they do not have octet of electrons. Now we want to satisfy the octet. We want to do it logically. Okay, so it will be easy if we first satisfy the octet of the element on the outside, and then if we have any electrons left from the balance after fulfilling the octet of the element on that side, we put the remaining, the balance electrons on the central element, because all the electrons must be used. So how many electrons will this oxygen require to have octet, this oxygen, the one on the outside? How many electrons will it require to have octet of electrons? It requires 6. So we put them as a pair, okay? 1 pair, 2nd pair, and 3rd pair. We have used 6. How many are we left with?
6.
Now, how many electrons will this oxygen need? How many electrons will this oxygen? As lone pair, 1 here, another here. Do we have anything left?
Yes.
Yes, because we have
2 more.
10 of them. So the remaining 1 we put in here. So Is it okay? Now, when you look at this, you can see this oxygen as well as this oxygen. These two, they have octets. Okay? They are happy. But the nitrogen in the middle has only 6 electrons. No octets. All the elements must have octet of electrons, so long as there are electrons. So now, as you can see, we can have 2 possibilities of fulfilling the octet of this nitrogen. It is possible that we can do it like this, okay? Or we can do it like this, okay? So we can have 2 structures. So let me draw both the structures, okay? So let's see what comes out of this. So if we do that, we'll have H, O, and then nitrogen. So there will be a double bond between the oxygen and the nitrogen. We'll have a lone pair of electrons on this oxygen. And then the central nitrogen will have a lone pair of electron, which is not involved. And then we have this oxygen. See, when you look at this structure, this oxygen has got 8. The nitrogen in the center has got 8. The oxygen in the outside also has got 8. Now let's look at when we use the lone pair of electrons on this oxygen to fulfill the octet of the middle nitrogen. So let us see what happens. Now, of course, this side is not going to be affected. You have a hydrogen, we have oxygen. On that oxygen, we have 2 lone pair of electrons. We have the nitrogen in the middle, which has got a lone pair of electrons. Then we form a double bond oxygen. And then since we have used 1 lone pair, we still have 2 more lone pair of electrons remaining. See, as you can see, we can do it this way using the green or the purple. So we have 2 structures. Which one is the correct one? We have to investigate. If you investigate, you will see on this one, this oxygen is +1, this oxygen is -1. We have a positively charged oxygen and a negatively charged oxygen. At the end of the day, the molecule is neutral. +1 - 1 is 0. It's like 1 - 1. But if you look at this one, none of the elements in this molecule are charged. So which one is the correct Lewis structure? The one in purple
The
or the
one
one in
without
green?
a charge.
The one in green is the correct. This is the valid Lewis structure for the molecule. Iko sawa? Is it clear?
Yes.
Okay, thank you.
Yes.
So guys, so at the end of the day, at the end of this lecture, if you get it wrong in the cut or the exam, when I ask you to draw Lewis structure, you can't forgive yourself. You can't forgive yourself. Because if there's anything that is not clear, you have a chance to ask now. And be attentive and follow. And by the end of this, you will have no issue at all in drawing Lewis structure, formal charges, all these other things that are related to drawing the structure of molecules. So now let's look at the structure of sulfuric acid, H2SO4. How many acidic hydrogens do we have in sulfuric acid? Do you know how many acidic
Two.
hydrogens? We have two acidic hydrogens in sulfuric acid. Anyway, so this is
You
sulfuric
have
acid.
two.
But do you really know the structure of sulfuric acid? Do you really know? Okay, so there you are
Yeah.
equipped in. You don't know. You only came to know about it because of SH102. So Lewis structure is very, very, very important because sulfuric acid is a diacid. It has got two acidic hydrogens. It is also very strongly acidic. The reason why it is a diacid, the reason why it is a strong acid is because of its structure. If you don't know how to draw the Lewis structure of sulfuric acid, you cannot tell whether it is an acid in the first place, whether it is a diacid or not. So drawing the Lewis structure is very, very important. So step one, arrange the atoms. I don't have to tell you that the most electronegative one should be at the center. So in sulfuric acid, of course, we have hydrogen. We keep hydrogen on the outside. So we have sulfur and oxygen. Which one should be at the center?
Sulfur.
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 Because sulfur is less
Sulfur.
electronegative.
Less
It is not,
electronegative.
you are not tossing, okay? Sulfur is, okay? So sulfur will be at the center. So let me put the sulfur at the center. See, we'll forget about the hydrogen. The hydrogen will be on the outside. Now, sulfur at the center. And this sulfur will be surrounded by oxygens. So we'll have one oxygen in here, another oxygen here, another oxygen here, another oxygen in here. Okay? And then the two hydrogens bonded to these oxygens, okay? The hydrogens cannot be. You can have a hydrogen on this side, you can have a hydrogen on this side, you can have hydrogen here, you can have hydrogen up here, you can have the hydrogens up and down, like that. All the same, we have two hydrogen atoms that are bonded to these oxygens, okay? So let's just make it symmetrical, and let's put one of the hydrogen in here, the other one on this side. It is possible you could put both of them, like one of them here, connect to this oxygen, the other one in here, or up and down, it does not matter. The most important thing is that we have the two oxygens bonded to hydrogen, okay? I've just taken attendance, and those who don't attend, if the dean says you are still first year next, don't question them, okay? You reap, you know what, isn't it? It does not come from anywhere. Okay, so this is how the atoms are arranged, and then the second step is to count. Step 2. Count the total number of valence electrons.
Excuse me, sir.
Yes.
I think your
Hello?
screen is not moving. Your screen is not moving. I don't know whether I'm the one who's experiencing that alone or the rest are also.
I know for sure. The rest will tell you everything is okay. I know for sure. Isn't it true?
Yeah. Everything is okay.
Iko sawa, because you know my brother, it's just this connection problems. Okay, I'm really sorry, but I will share the slides and also the discussion. I will be very happy if the screen moves. You see the screen as we go along, but sometimes it's very unfortunate because it's not from my side and it's not also my wish for this to happen. Okay, so we have 2 hydrogens, 4 oxygens, and 1 sulfur. Isn't it true? So we have the 2 hydrogens, 2 times 1. We have 2 electrons as a result of the hydrogens. Oxygen, there are 4 of them. 4. The number of valence electrons of oxygen are 6. 4 times 6 electrons. In total, 24 electrons. How many electrons do we have on sulfur? Hello?
6.
6, because of sulfur is just below oxygen. So these are 6 electrons. Therefore, the total number of electrons of these are how many?
32.
32 electrons. So let me pick this one. And the 32. And the 32 electrons we got from the previous step, okay? So we have these and 32 electrons, okay? So now step, what is it? The next step is step 3, okay? Step 3. So let me do it differently. Add bonding and non-bonding electrons, okay? So bonding and non-bonding electrons. So first we form a bond. So we put a line between all the atoms, between hydrogen and oxygen, yeah. Between this oxygen, sulfur, sulfur and oxygen, sulfur and oxygen, sulfur and oxygen, and hydrogen. That's what we do. So how many electrons are used now?
12 electrons.
12.
Are you sure? How many single bonds do we have? We have 1, 2, 3, 4, 5, 6, okay? So 6 times 2, we have used 12 electrons, okay? 12. Balance. How many is the balance?
20 electrons.
A lot of electrons, isn't it?
20.
20 electrons. What do we do with these electrons?
On lone pairs.
So we use them as lone pair, okay? Because if you, let us just look at the sulfur. The sulfur, it has got 8 electrons. Okay, you might say the octet of the sulfur is fulfilled, so the sulfur will not need. Even if it needs, we'll not worry about it first. What we'll worry about is the element that are on the outside. So now we have the 4 oxygens, because the hydrogen is okay, it has got duet of electrons. We have the 4 oxygens whose octet is not fulfilled. This one has got only 4 electrons. This one has got 4 electrons. This one has got only 2 electrons. This one has got only 2. Therefore, we must fulfill the octet. So let us just please mute. Let us first fulfill the octet of the oxygen, this oxygen, the ones that are not attached to the hydrogen. If you look at them, they only have 1 bond. Then as a result, they only have 2 electrons. How many electrons will they need to have octet? 6. So we have this 32. Okay, we are not going to add more electrons than what we have. So we'll count. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Then when you look at the oxygen, this one requires 2. So we have used 12, 13, 14, 15, 16, 17, 18, 19, 20. We had balance of 20, and then we can count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Now, let us look at this. Let me copy it, take it to a new slide, and then we investigate what we have. Because you have to investigate and make sure what you have drawn is a valid Lewis structure. Now, guys, tell me, is this the structure of sulfuric acid? Huh? Because you know what you see, we had how many electrons? 32. We have used all the 32 electrons. Then when you look at them, the hydrogen has got duet. These 2 oxygens, they have 8 electrons. Then this oxygen has got 8 electrons. Even the sulfur in the middle has got 8 electrons. All the electrons are used. But is this a valid Lewis structure?
No.
Is it a valid Lewis structure? I want reactions.
No.
Me, I want to listen to the yes first before the no. I want to listen to the yeses first. Anyone who says yes? Huh? Hello?
Excuse me, sir.
Is there only one person in the class?
It is valid.
It's a valid Lewis structure, isn't it?
Yes.
Now, one of the things, of course, to have a complete Lewis structure, of course, we have to put the charges, isn't it? We have to also put the charges. on the atoms. So because the formal charges are important, isn't it true? So if you look at this oxygen, what is the formal charge on this oxygen?
-1.
-1.
-1.
The same is to this one, okay? How about this oxygen?
Stable.
It is
Neutral.
-5 or neutral?
It is neutral.
Neutral.
Okay, satisfied.
Neutral.
Now, I want you to tell me what the charge on this sulfur is.
Positive 2.
2.
Huh?
Excuse me, sir.
Yes.
I don't think this is a valid Lewis structure because sulfuric acid is neutral, but the structure shows that it is negatively charged.
Now. Okay, now tell me what is the charge on the sulfur. Before even calculating, before we even as I agree with you,
Positive.
said sulfuric acid must be a neutral molecule, isn't it?
True. That's true.
So now these two are -1 plus -1 -2. For the sulfuric acid to be neutral, the sulfur must be +2. Let us prove it. Let's prove it. So let me calculate the formal charge on the sulfur. Okay? Number of valence electrons of sulfur, just like oxygen, is 6.
6.
Yes. Number of lone pair of electrons you see on the sulfur is how much? How many are they?
0.
0.
0. Of
Plus
bonding 6.
half. How many are the bonding electrons?
8.
Because there are 4 bonds, 8. Now let us do the calculation. This is 6 minus 4, which is plus 2.
2.
So the charge on the sulfur is +2. Hello? Now, let me take it to another page and we talk about this, okay? This is what we have. Now, I want you to look at these bonds critically, okay? Let me put a different color. I want you first to look at this bond and the lower bond, okay? Similarly, I want you also to look at the 2 sulfur oxygen bonds. What do you see is -1 +2 -1. There is separation of charges between the sulfur and oxygen. Separation of charges means having positively charged and negatively charged atoms on neighboring atoms. So we have here separation of charges. In here, we also have separation of charges. As a result of this separation of charges, this molecule is unstable. Okay? So, Because of this separation of charges, this is not a valid Lewis structure for sure. Now, what is the correct structure? Because let me tell you the other thing. If this was the structure of sulfuric acid, if this was the structure of sulfuric acid will not be acid. It will not be acidic. You know what acid means? Acid is something that gives it is hydrogen. So this hydrogen must be given out, must be picked by a base. This hydrogen must also be picked by a base. It is not easy or very easy for a base to come and take this hydrogen or this hydrogen. It might be possible with a lot of struggle to pick these hydrogens. But as you know, sulfuric acid is a very strong corrosive acid, very strong acid. That means it is easy to pick these hydrogens. Sulfuric acid gives these hydrogens very easily. So this is not consistent. This property is not consistent with the structure. Now, let us draw the Lewis structure for sulfuric acid, the correct Lewis structure for sulfuric acid. There is nothing wrong we have done in what we have done so far. So we'll have hydrogen, we'll have oxygen, we'll have sulfur, we'll have oxygen here, oxygen here, hydrogen here, and oxygen here. 2, 3 lone pair of electrons on the oxygens. Now what should happen? We must make sure the molecule, as much as possible, does not have charges. As much as possible. We must also make sure, as much as possible, there are no separation of charges. You remember sulfur? It has an expanded octet. Sulfur can have more than 8 electrons. Okay, because sulfur is in group, what is it, in period 3 of the periodic table, because in period 3, in addition to S and P orbitals, in addition to the S and P subshells, we have the D subshell, which can also be filled. So as a result, sulfur can have more than 8 electrons. So what's going to happen? To cut the story short, this one will be used to form a double bond here. This one can also be used to form a double bond in here. So the structure of sulfuric acid is H O S double bond O, double bond O, O H. Of course, you have to put the lone pair of electrons. So when you look at this structure, of course, without even doing formal charge calculation, you will see all the 4 oxygens are neutral. Let's calculate for the sulfur, okay? Let's calculate for the sulfur. Formal charge on the sulfur in this particular case. We have 6 valence electrons minus. We do not have any lone pair of electrons on the sulfur, 0, plus half the number of bonding electrons are 1 bond in here, 2, 3, 4, 5, 6. We have 6 bonds. 6 times 2 is 12. So when you calculate this using mathematics you've learned in preschool, you'll find the formal charge on the sulfur is 0. Then all the atoms in sulfuric acid are neutral. So this is the Lewis structure for sulfuric acid. Is it okay?
Yes.
Okay.
Now, so based on, I've just picked some questions, okay? From now on, I will not pick questions. I want you to pick, I want you to tell me, I have a problem with this question in our assignment. I have a problem with this question somewhere. If there's anything that is related to our syllabus, I will answer, okay? It is not good for me to bore you with details. I want to solve your problems, okay? So I want you to tell me that you have a problem with this, can we do it, okay? It will be better that way. And I'm willing to solve it if you can help me, because you must be involved. So let us draw the Lewis structure of this. Draw Lewis structure. We don't want any story. We want to draw Lewis structure. At the end of the day, it does not matter whether this molecule is going to have charges. Some of the atoms in the molecule are going to be charged, or whether there is going to be resonance. We don't care. We just follow the steps in drawing Lewis structure. And then whatever result we get, that will be the result. Because so you don't need to worry whether there is resonance or whatever. Don't worry about that. The result will tell us. The finding will tell us. So I'm going to follow the steps in drawing Lewis structure. Step 1. Arrange the atoms. Okay, that's step 1. So in this particular molecule, we have 3 oxygen atoms, and then these 3 oxygen atoms in ozone are joined to one another linearly. It is not a cyclic molecule, it is a linear, an open chain molecule. So we have oxygen here, another oxygen here, and another oxygen here. These are how the atoms are arranged in oxygen. Then step 2. Step 2. Count the total number of valence electrons. Okay, so we have 3 oxygens. 3 times 6 is 18 electrons. Okay, that's what we have. So let's go to the next step, step 3. Add bonding and non-bonding electrons. Okay, so we have determined this is how the atoms are arranged. We've also determined the total number of valence electrons are 18. 18 electrons, okay, which we have determined from step 2. And this we have determined from step 1, how they are arranged, okay? So now we have 18 electrons. This is how the atoms are arranged. First, we form bonding. So we use the electrons to form chemical bond. That's what we do first. Number of electrons used are
4.
4.
4.
Balance
14.
14. Now, what do we do with this? Okay, let me take it. Let me draw it on the next page. Okay. So remember, we have 14 electrons left. So we have oxygen. Okay, let me do it. Let me do it in the middle. Okay, first. Okay, let me see. We have oxygen and another oxygen and another oxygen. We have 14 electrons left. So first we fulfill the octet of the elements on the outside because none of the elements have octet. The one in the middle has got 4. The ones in the outside, they've got only 2. So we have to use this remaining 14 electrons to fulfill the octet of all the atoms. So we have 2 oxygens on the outside. How many electrons will these oxygens require in total to have octet? The oxygens on the outside,
12.
how many in total will they require? Both of them. 12. How many electrons will be
6
left?
electrons.
How many will remain?
2.
2.
So let me just put the 2 in here. Let me just put the 2 in here. Then we know what. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, we have used all the electrons. Now, let us look at this poor guy in the middle. This oxygen. No octets. That's all.
Yes.
So we must fulfill the octet of that oxygen. How do we do it? How do we achieve
By
that one?
forming
Like what? Are you a left-handed person or a right-handed person? Hello? Are you right-handed or left-handed? Hello?
Right-handed.
Right-handed. Okay, so let me start from the right. Okay, let me use this right to do like this. I am also right-handed person like you, but I know I have so many friends. Probably even you have some friends who are lefty, isn't it? And then those ones they will say aina, apana. Me, I like doing it from this side. So the good thing about this, compared to the previous one we have seen, that these 2 are oxygen atoms, isn't it? And both of them have got 3 lone pair of electrons. There is no difference between the 2 oxygens. So it is possible to equally use the electron on the left or the electron on the right to fulfill the octet of the oxygen in the middle. So let us first do it from the left. So what's going to happen? You have that oxygen. It has got 2 lone pair of electrons. Then that is bonded to this oxygen, which has got 1 lone pair of electron. And then this one. No, this is a double bond, isn't it? This is a double bond. And then we have 3 lone pair of electrons. The other one, the other possibility is for the oxygen on the left to remain the way it is with 3 lone pair of electrons. And then we have this oxygen single bond. Okay. Then double, please mute oxygen, because unmuting is just a click. Okay. It does not take a lot of time. So it is better you remain muted. So these are the two possibilities. And then let us compare the two structures so that we can have preference. Okay. So let me have A. Let me say this one is A and the other one is B. If I determine the formal charges, I will find that this one is 0. This one is +1, while this one is -1. Similarly, this one is -1. The one in the middle is +1. The one on this side, it is 0, neutral. Okay, neutral. Is there a difference in terms of charges between the two? None, isn't it?
No.
So what it means for this particular molecule, we have two possible structures, A and B. So these two structures, A and B, are resonance structures. And none of these, either A or B, is the structure of the molecule. Ozone is not an A. Ozone does not look like B. It does not look like any of this. Ozone is the average of the two. Ozone is the resonance average. Ozone is the resonance hybrid of these two structures. See, now, we did not force this. Did we force? Did we start? Did I ask you to draw resonance structures? Not at all.
No.
We just arrived at such a situation. So resonance will come in as a theory when we fail to write or to represent the structure of a molecule with a single structure. When that happens, we have resonance. So we have these two. So if you look at the resonance hybrid of this resonance hybrid, of this, you will see, of course, we have oxygen, single bond oxygen, another single bond oxygen. When you look at the oxygen in the middle, the central oxygen, the oxygen at the center, what is the charge on it on both cases? What is the charge on the oxygen at the center? In both cases,
+1.
it is
+1.
+1. So in the resonance hybrid, we should expect to have a +1 charge on that oxygen. It has got a lone pair of electrons. The other thing I want you to notice, just look at the oxygens on the outside. The oxygen on the outside. What is the minimum number of electrons that you find in both oxygens? What is the number of electrons you find in both oxygens? How many? In each of them.
Four electrons. Hey.
See, these four electrons.
8 electrons.
Like here, no. See, like this one. These ones are common to both of them. Because in this oxygen, I have 2 lone pair of electrons, isn't it? Even when I come on this one, I have 3, so these 2 are there. If I come to this oxygen, I can see 6, at least 2 are there. On this one, there are only 2 lone pair of electrons. So these ones are common. So you'll put those ones. We have no problem with those ones. Now, if you look at this oxygen-oxygen bond in A, this one is a double bond in here, isn't it? But I cannot put a double bond in here because in its other resonant form, the same oxygen bond is single. So I cannot put it as either as a single or a double bond. If I say it is single, one of the resonant form has a double bond. If I say it is double, one of the resonance form of the same molecule has got a single bond between these two oxygen atoms. The same to this other oxygen bond, single and double. So they are intermediate between a double bond and a single bond. So what we'll do to represent that, we just put dashed line. Okay. And this is the resonance structure of ozone. Is it okay?
Yes.
Is it clear?
Yeah.
Do you remember what I started with? I said I will discuss
Yes.
with you these ones, okay? Me, I have finished. You tell me, which problem do you want me to look at? Referring to your assignments in SOMAS or anywhere related to whatever you want me to discuss.
Excuse me, sir.
Mm-hmm.
Resonance in cyclic alkenes, alkenes, I mean.
Mm-hmm.
Yes,
Which
I have
particular
a problem in that section.
because there is no problem at all. You see, I don't want you to panic about things. Okay, so let me pick one, and I discuss about it. I talk about it. Mm-hmm. So first, let me look at a simple thing. And I like simple things because through simple things, I can teach you things with clarity, and then we can complicate it once you understand the simple thing. So let me just first have a discussion on this. And if you know this, if you know how to draw the resonance structure of this, you can do for many others. Okay, so first resonance structure for this. Draw all the resonance structure. See, what I want you to know, cyclic means, if you know this, it's just that this carbon and this carbon are joined. You know, the thing has become a cycle. Nothing else, okay? So it is better to understand basic concepts. Now, before I tackle this one, let me share with you the simplest thing. If you look at this molecule, if you look at it, just forget about the other details, okay? Forget about the other details. And let me do this. Forget about the other details, okay? Let's just focus on this, okay? I'm not talking about these other double bonds, these other methyls or whatever. Let's just focus on this. Then let me draw the resonance as a result of that. Let me not worry about other things. So if I know how to draw the resonance of that, I can draw all the rest. So if I have something like this, which is what I have highlighted is, okay? If I have something like that. I've forgotten about all the other things. Just that. What is the resonance form of this? What are the resonance of this? When you have something positively charged, what I want you to know. This, you have a positive charge. Okay, this positive charge is on a carbon. Is on a carbon that has got a single bond with a carbon that is involved in a double bond. So we have a double bond, single bond, and then on that carbon that has got a single bond with this double bond carbon, we have a positive charge, okay? You can identify this in many different structures, in aromatic rings, in cyclohexane, in many things, okay? That's what it is. So like here, we have many complicated things. These are decorations. If you don't understand this simple thing, you will not understand this. Now, when you have a system like this, the resonance form of this will be is for this double bond, for the electrons of the bond, the pi bond, to be used to form a double bond with this carbon. So when that happens, what we are going to have is we'll have a double bond in here, and it is this other carbon which is going to be positively charged. So this one's called allylic, okay, which I have discussed in class. Allylic carbocation, okay. Sawa, I don't want you to do anything, just understand this. Even if it takes 30 minutes, I don't want you to try to solve this problem or any other problem. Just focus on this. Because if we were to draw the structure of a molecule, this one was, it is C3, it has got 3 carbons and 2, yeah, and H6. Actually, this molecule is C3H6 plus. If you to draw the layout structure of this, you can draw either this one or that one, 2 different possible structures there for resonance, okay? So, as I have always told you, when you only need to draw the Lewis structure of one of the resonant form. The other one can be generated from the same through use of curly, curved, or pushing arrows. So you only need to show this electrons of this double bond can be used to form a double bond in here. When these electrons are used to form a double bond in here, this carbon becomes positive. So the positive charge, sorry. Yeah, my mouse is misbehaving. Oh. Hey, sorry guys, it is the devil. And the positive charge that was supposed to be, that was in here, through resonance, it goes into this one. So if I have to draw this is the resonance, if I have to draw the high resonance hybrid, will be that any of these carbon-carbon bonds can be between a double bond and single bond. So I will just be drawing this like that. And on this one, I will have a +2 charge. On this other one, I will have a +2 charge, because in this molecule, the charge we have is +1, and then that +1 is shared by this carbon and that carbon, and equally. So this is +½ this is +½ Is this one clear? If this one clear, I will show you how we can draw the resonance structure of that and many other things. Is it okay?
Yes.
Yes.
Okay. So let me draw the resonance for this, okay? So that I want you always to recognize this thing, okay? Double bond, then you have a carbon-carbon single bond. On that one, you have a positive charge. Then these are the two resonance of that. I want you to recognize that. Now, let us go and look at this molecule. Okay, so I will just draw it. You see, what you should know, that we have this double bond, single bond, and then on that, this carbon, we have a positive charge. You should not forget, when you have something like that, what you do is, you use these electrons of the double bond. Now use those ones to form the double bond in here. Then when that happens, what you will have is, the rest of the structure will remain the way it is, because we have not interfered with it. We have not done anything to the rest of the other part of the molecule, so the way they will remain the way they are. And I'm saying this because when students draw resonance structure, when the thing was happening here, but they do something else in here, I don't know what. So I want you to focus on what you have done, and then only change what has happened, okay? So this is one, no. Okay, sorry. Because it's good to number these things so that you are not confused. So for our purpose, let me just say 1, 2, 3, 4, 5, 6, 7, okay? Let me just do that so that we don't get lost. 1, 2, 3, 4, 5, 6, 7. So we have a double bond between carbon number 3 and 4. We have a double bond between carbon number 5 and 6, which we have not interfered with. Now, this one, oh, sorry. So the one between 5 and 6, of course, we have now used it to form a double bond between carbon number 6 and 7. And then we have these two methyls. So what happens? What will we have on carbon number 5? What are we going to have on carbon number 5? Hello?
+1.
Positive charge.
Okay, we are done with this part. You see, we did this and we formed this, isn't it? Now, can you look at this one? This part. Let me bring for you your this highlighter so that you can see. You can see. Can you see this section? We have a double bond, single bond, a positive charge, isn't it? So what do you expect as a result? This one also there will be resonance. This double bond will come here. We'll have another resonant form. This. So we draw the structure like this, like that, like this. So I don't want to be lost again. Let me just put these numbers which can guide me. I have 7 is this one. Then I have that one and that one. The double bond is in here, you see. I have not done anything with it. The only thing that has happened now, we'll have a new double bond between carbon number 4 and 5. On number 3, what do we have? What will we have on number 3? Hello?
Positive charge.
We'll have a positive charge. Okay? Are we done? Then I want you to see, I don't want you to be blind or one-dimensional person only. Then I want you to see this. What do you see in here? We have a double bond, a single bond, and a positive charge, isn't it? So, similarly, you should expect this double bond to be used to form a double bond in here between carbon number 1, between carbon 2 and 3. So now what we'll have is let me write 1, 2, 3, 4, 5, 6, 7. This, and between 6 and 7 we have a double bond. Between 4 and 5 we have a double bond. Now we have a double bond between carbon 2 and number 3. Now the positive charge goes to this carbon. Okay, we were able to do all this because of this. Okay, this thing was repeating itself as you go along, nothing else. So these are all resonant forms. So this molecule has got 1, 2, 3, 4 resonant forms. 4 resonant forms. You can even draw. Please mute your mic. Hello. You can even draw the resonance hybrid for this. Okay, let us draw it. Okay, let us draw the resonance hybrid for this. This, that. I don't want to get lost. You have 1, you have 2, you have 3, you have 4, you have 5. I will not have space if I draw it like that. I will not have enough space. So let me make it smaller. This is 1, this is 2, this is 3, this is 4, this is 5. This is 6. 1, 2, 3, 4, 5, 6. This is 7, and I have this 7. Okay? No, I made a mistake, and you are not even helping me. Okay, because I counted wrongly. I was supposed to count from here. 1, 2, 3, 4, 5, 6, 7, and this 3. Okay. Now tell me, on how many carbons do we have a positive charge in the resonance? Okay. On number 1, on which carbon is the positive charge? Huh? In resonance 1, on which carbon is a positive charge? Hello?
Carbon 7.
Carbon number 7, okay? So the positive charge has gone to, 7, is on 7. On resonance number 2 is on which carbon?
Carbon 5.
Carbon number 5.
On resonance number 3, on which carbon is the positive charge?
Carbon number 3.
3.
On resonance number 4, okay, so let me call it the other carbon, okay? All the same, it is on, let me call it 1 prime, okay? For our purpose, okay? So the other one, it is on 1 prime, isn't it? Cindy?
Yeah.
What is the total charge on the carbon, on this molecule? What is the total charge on this molecule? Only?
Plus a half.
No, what the total charge on the molecule?
Plus 1.
That's 1. That's 1. It's a positive 1 carbocation. But this positive charge, through resonance, it has gone to how many carbons? To 4. So these 4 carbons will have, because these 4 carbons are the same atoms, carbons, so they will share the positive charge equally. So the positive charge on these 4 atoms is a quarter. Quarter plus quarter plus quarter plus quarter is 1. So on number 7, you put plus a quarter. Okay. On number 5, the charge is plus a quarter, or 0.25. On number 3, the same, it is plus a quarter. Then on number 1 prime, the same, plus a quarter. As you can see, number 2, number 4, number 6, and these other carbons, they don't have a charge, because the charge through resonance did not go to those carbons. They're neutral. But the positive charge, that plus 1 charge on the molecule, is shared by 4 carbons. Carbon number 7, carbon number 5, carbon number 3, and carbon number 1 prime. Is it okay? Saso?
Yeah.
Yeah.
Now, this is one aspect. Now, the other aspect I want us to look at is a double bond. Carbon-carbon double bond, okay? I want you to tell me, in this first one, between which carbons do we have a double bond? I know it will be very complicated. Of course, it is possible to trace, but let me just be satisfied that we have a double bond between 2 prime and 1 prime, isn't it? Between 3 and 4, between 5 and 6 in this one. If I come to resonance number 2, I don't have a double bond between 5 and 6, and instead have a double bond between 6 and 7. If I come to resonance number 3, the double bonds, see, in resonance number 2 have a double bond between 3 and 4, but between 3 and 4 now it's a single bond, but the double bond instead is between 4 and 5. If I go to resonance number 4, I do not have a double bond between 1 prime and 2 prime, and instead I have a double bond between 2 and 3. Therefore, we should expect a double bond between 1' and 2'. So let me use a different color. I'm going to finish, okay, right now. Like this, we have a double, so you put a dashed line. Between 2 and 3, as you can see here, we have a double bond, dashed line. Between 3 and 4, in here, we have a double bond. Between 4 and 5, 4 and 5 here, 4 and 5 here, we have a double bond. Between 5 and 6, let us see if we have a double bond between 5 and 6. As you can see here, we have a double bond between 5 and 6. Between 6 and 7, of course, 6 and 7, we have a double bond here, a double bond everywhere. So these bonds, which have indicated with a green dashed line, are intermediate between a double bond and a single bond. Okay? If you understand this concept, you can draw the resonance structure of anything, I can, even for you to practice, I will give you this, okay? Just for you to practice. Let me just see if I can. So let me put a positive charge here, double bond and double bond. I want you to draw the resonance structure of this. For now, okay? Then you guys think about it, you know, from now on until the end of our exam on the 15th. I will avail myself for a discussion. If you have any problem, I will be with you until you get tired of me. Until you say, we don't want to see you anymore. Okay? To make sure I give you a chance to understand this concept so that when you go for your exam, you go when you are ready. Is it okay? Sasawa?
It's okay, sir.
Yes.
So
Yes.
not this coming week. The other week we'll have. Let me see on which day. On 31st, on Monday 31st, we'll have a catch. Okay. Is Monday 31st okay with you?
Yes.
Because by then you'll have done all the manenos, isn't it? Okay.
Yes.
So, but in the meantime, I'll be here to guide you. Okay, I'll be here to guide you. It is only you will fail to ask me a question, not me failing to answer your questions. Because